Hey guys, it's Andre from High Performance Academy here. Welcome along to another one of our members' webinars. It's been a little while. We have all been all around the world probably pretty much suffering the same fate, which is some form of quarantine, self-isolation. We've been in about a 5-week countrywide lockdown, which for the most part meant that we couldn't get into our workshop, which is why we've been sadly missing in the webinar department. However, just recently, New Zealand's dropped back a level. This allows us some restricted access to our workshop, so we're back into it. We're trying to make the most of it and also trying to catch up on a little bit of lost time. So first of all, excuse me, start by saying hopefully everyone out there watching is staying safe in some pretty unprecedented times, but I don't want to dwell on all of that nastiness. Let's get into something to take our minds off it a little bit more interesting. Today's lesson, we're going to be looking at some of the basics of data logger setup, some of the fundamentals, and we're going to be focusing on the setup side of the data logger, making sure that everything in the data logger is configured correctly so that you're going to get good, solid data when you come off the racetrack, no matter what kind of racing you're personally interested in. Before we do go into that though, with 5 weeks that we've been missing in action, there's a fair bit to cover off. Obviously we haven't been able to get into the workshop too much, so we are a little bit behind in some of our projects, but I did want to cover off what we have been doing. Excuse me. So we're going to start with our FD3S project car, and there's been some reasonably exciting developments on that. We're getting dangerously close to having this thing actually ready to start, hoping that by the end of this month we should be in a position to get it up on the dyno. But for those who have been following the project for a while, you'll have probably heard me talk about this a couple of times now. Let's just jump across to my laptop screen, and this is a shot of the upper inlet manifold, and the problem that we've been sort of thinking about is what we can do with the conventional cable throttle body. We have been wanting to switch it to drive-by-wire, and just to cover off and get everyone up to speed who hasn't been following along, one of the problems is that while yes there are kits on the market to adapt a single drive-by-wire throttle body onto the FD3S inlet manifold, I didn't really want to go down that path. The reason being that there's essentially 3 butterflies behind inside of that throttle body. Obviously we can't see that right now, and they run as sort of a primary and secondary style. Their opening is synchronized. They don't all open at the same time, and I wanted to retain that if we could, so going to a single throttle body really wasn't going to cut it for me. What we looked at doing was using something like this, which is a remote mount drive-by-wire throttle motor I should say. This is specifically off a BMW S54, so this can drive a conventional throttle body using a pushrod mechanism, so it seemed ideal. The problem is that there weren't a lot of opportunities or locations that were convenient to mount that. I'm a bit OCD. I didn't want it to look ugly, so that's one of the drivers that we were considering. So back to our photo here on the laptop. One of the options we had looked at was mounting it down underneath the upper inlet manifold. That's about the only place that sort of made any sense. However, it also made perfect sense to mount our IGN1A coils there, so not enough room for both of them, and I'd basically at that point given up on the drive-by-wire idea. However, we also needed to remove the air conditioning from the vehicle in order to, because we couldn't easily run the aircon with the V-mount. Possible, but just not easy anyway. Different conversation for a different day. And Brandon actually had the great idea. Again, it's a little hard to see in this photo, but basically down here is where the aircon pump normally fits to the side of the 13B block. We're obviously removing that because we don't have the aircon, so it actually gave quite a nice location for that big bulky drive-by-wire throttle motor. And while again we can't really see it, basically we could run a push rod directly from the drive-by-wire throttle motor up to the throttle body, so this all looked like it was actually going to work. And this got us into a situation which I've been in the past and never really had any easy solution, where we need to make up a bracket in order to adapt that throttle motor onto the air conditioning mounting bracket. And we're a bit OCD, so we wanted to make a nice job of this. So this is where Brandon's newfound skills on Fusion 360 came in, and he's put himself to work on Fusion 360 over the time we haven't been able to get into the workshop. So again, looking at my laptop screen, this is a model he made for a 3D printed part. So obviously that in that render there, it's in alloy, but we wanted to obviously design this and then prove that it was going to fit. So this adapts the drive-by-wire throttle motor onto that air conditioning air conditioning mount. So what he did was, using our new 3D printer, printed that out. For those who are wondering, this is a Creality CR10S Pro, I think, off the top of my head. I'm figuring that'll probably come up in the questions, so there you go. And that allowed him to print out this little test piece here. So we'll have a quick look at this under our overhead camera. So this is printed out of plastic, and before you ask, no, we're not going to leave it in plastic, even though it's actually surprising just how much strength there is in this. But the idea with this is the 3D printer allows us to quickly prototype that and actually prove that it fits. Quite often you're going to find that after you've designed some components in the likes of Fusion 360 or SolidWorks, when you actually go to fit them, there's some sort of unforeseen problem or fitment issue. So it allows you to fiddle around with that model before you actually go to the expense of having that component then designed and sorry, not designed, actually made on a CNC mill. So we did, once he was happy with that, obviously this little prototype here didn't have those lightning holes, probably not going to really move the needle in terms of the overall weight of the FD3S RX7, but hey, if you've got the opportunity to easily add some lightning holes, why not? So again, if we'll just switch across to my laptop, I've got a colleague up in Wellington who has a CNC machine, and he's just produced that part for us. So we're already confident, obviously, that that's going to fit when we get that part back. So that's the first part. That basically adapts the drive-by-wire motor. I'm actually not quite sure exactly how that ends up working, but that adapts onto the drive-by-wire motor and then mounts onto the air conditioning bracket. However, there's a little bit more to it than just that as well, because we also needed to make sure that the bell cranks for both the throttle body as well as the drive-by-wire motor, the motion ratios were aligned and everything was in the right place. So again, Brandon got out the 3D printer and Fusion 360. So if we jump to our overhead camera, he's removed the factory drive or bell crank off the drive-by-wire motor and designed this. Again, obviously the finished final product isn't going to be in plastic, but it's also got a range of different mounting locations which allow us to change the motion ratio and make sure everything's going to work. At the same time, the same sort of performance was done to the throttle body, and you can see we've got another bell crank that's been designed there. So obviously this is a bit of a work in progress. I'm not 100% certain that everything is going to work exactly how we expect, but right now it's looking pretty good, and we've basically got the ability to run a straight rod between the drive-by-wire throttle and the throttle body there. We're just using some rod ends at each end of that to allow a little bit of angular misalignment. Seeing as Brandon was getting pretty handy on Fusion 360 and with our 3D printer, so the other problem we had to get through was we decided we were going to remove the factory Mazda oil metering pump. So for those who aren't aware, the oil metering pump is a stepper motor drive essentially that injects oil into the rotor housing. So most but not all competition rotary engines tend to do away with this and run premix instead, where the oil is actually mixed in with the fuel. There's pros and cons on both sides of this, but this is the way that we've decided to go. However, this requires us to also blank off where this bolts to the block. So again, if we'll look under the overhead shot, we've got the little drive here, and you can see there is a groove in this for an O-ring which actually seals to the block. So it's important to have that in place, otherwise we're going to end up with an oil leak. So again, Brandon designed up, I think think I've got a photo of that. Yeah, if we jump across to my laptop screen, pretty simple little bracket there, or little plate with that O-ring groove mounted in it. And again, once he was happy with the design in Fusion 360, printed that out. Doesn't take very long to print these either. I think this one was about 15 minutes from memory. Able to check that that O-ring groove is correct. The O-ring sits in there. Obviously, you can bolt that to the side of the block and make sure that that fits. And again, once we're confident that that's right, we can send that file out to a CNC machinist and have it manufactured in aluminium. So just some of the advantages with having some of this equipment at hand. And the great thing about this as well is that a lot of this has actually come down in price quite dramatically. The Creality 3D printer that we've got, I think off the top of my head, is somewhere around about the $650, $700 US mark. So it's really a hell of a lot of machine for that sort of money. And if you need to produce parts that are bigger than that machine can actually print, you can split them in your design software and actually dovetail them together, so you're not limited just by the size of that machine. Moving on as well, we are getting stuck into some filming on some more course material. So again, we'll jump across to my laptop screen. That's our version 11 Subaru STI sitting there on our mainline Pro Hub dyno. And I'm actually going to be doing 2 worked examples on this car, which will be added into our practical reflash tuning. We're doing an open source worked example for that. And we are also adding in an ECU Master Black worked example into our practical standalone tuning course. We've had a lot of requests for ECU Master content over the time we've been operating, so we've finally got an opportunity to get that up and running. Once we've done that as well, we will be bringing out some members webinars on both the ECU Master as well as the open source reflashing. So I just want to really quickly dive into the open source stuff for those who aren't familiar with what that means. So open source is essentially a usually freely available software package that's used for reading and flashing the factory tune or calibration data out of the factory ECU. So incredibly cheap compared to the commercial systems. All you really need is the software, which, as I say, usually you can download for free. You are also going to need a USB to OBD2 interface. The one that I've got here, which is probably the most popular, is the Tetrix one. I'll just have a quick look at that under our overhead camera. So pretty simple there, just plugs into the OBD2 port, and then we've got a USB connection that goes to our laptop. So that'll allow you to interface the car to your laptop, and from there you can read the raw hexadecimal file out of the ECU. So we'll jump into my laptop screen. So there are a variety of software packages available. Right here I've got a package called EcuFlash, again freely available. RomRaider is another one that we'll probably use, and there's a low-cost software called ECU Editor as well. Essentially, it doesn't really matter what you're using, they all work in much the same way. So for example, here we've got our structure of all of the tables down the left-hand side that we have access to, and if we look, for example, here under our fueling primary open loop, we've got all of our parameters there. The table that we're most interested in here is our primary open loop fueling table. If we click on that, we can open that up. Click on it properly, we'll open that up, and these are our open loop air fuel ratio targets. We've got our engine load and grams per revolution on the horizontal axis, obviously our engine RPM on the vertical axis there as well. So this allows us pretty much the ability to retune the factory ECU in the same way the calibration engineers do it. And again, very, very cost effective compared to the likes of an aftermarket standalone ECU or compared to some of the commercial reflashing packages. There's pros and cons with everything though, and that's the open source software is no different. In particular, you're kind of on your own here. So you're not going to get a nicely bound user manual that tells you what all of the tables do and how to approach your tuning, and particularly for those just getting started out, it can be a little bit daunting. There are literally hundreds if not thousands of different tables and parameters inside a factory ECU, so a little bit hard initially to know what to do, particularly the way some of these factory ECUs work. So the commercial package, you buy it, you're going to pay a lot more money for it, but you've got the support from that supplier if you do get stuck. So those are the sort of things you need to way up. Also, sometimes no neatly integrated logging package here. So what we've been doing is we've been using EcuFlash for reading and writing. And this will also display all the maps as you've just seen there. You can do exactly the same with ROM Raider, but you still need an auxiliary component, EcuFlash, to do the reading and flashing. And then I've been using the ROM Raider logger. And in order to interpret the logs, just because I do use it a bit, I've been using the Mega Log Viewer HD software. And if we can just jump across to my laptop screen here, we'll just open up a file which hopefully has got some data in it. And basically you can decide what parameters you need to log for whatever task you're doing, and then you can see exactly what's going on. This is a ramp run on the dyno here. Obviously we've got our RPM up the top here. We've got in white, and this parameter here is our manifold pressure, our boost pressure. The one that I've been looking at for this particular part of the tuning process is here in green. We've got our target air fuel ratio, so this is what the ECU is asking for, and then in red we've got our wideband air fuel ratio data, so it gives us an idea if our tuning is actually tracking where it should be. So again, that's our open source reflashing worked example will be added into our practical reflash tuning course, hopefully in the next few weeks. Basically, as soon as I can get it filmed, we'll have that online, and then the ECU master will follow up pretty closely behind that. Now, just for our other two sister companies as well, for those who've been following, Racecraft, we've got a couple of courses coming out. I was able to film before our shutdown here a corner weighting course. We've got some practical examples to go into that, and that will be available. And we're also going to get stuck into 2 data analysis courses. We're going to be touching on some of the material that we're talking about today, but with the Racecraft, we're really focusing on the driver side of the data analysis as well as the chassis. So that'll be great for all of those who want to learn how to improve their driving out on the racetrack. As well with our ETS fabrication, online fabrication school, Nigel's been working really hard over in Australia on a TIG welding course. There's a few finishing touches being put on that, and that should be just about ready for consumption as well. We know that a lot of people have been looking forward to that, and it's going to be a great addition to what he's already got in there. Now, I'll just also pop over. There's been a fair bit going on, obviously, since we haven't been around for the last 5 weeks, but I just wanted to head across to my laptop screen and on our Instagram. Over the time the last week or so, once we were able to get back into the workshop, I was back into our 3UZ project for our Toyota 86 race car and stripping down our donor engine. And I just did a little Instagram I wanted to explain here. This is something that is unique to some of the Toyota engines. Well, Toyota actually kind of adopted this and ran with it with quite a few of their engines, so maybe saying unique isn't quite right. But this is the cylinder head here, and obviously it's a twin cam cylinder head, but while it's out of shot here, this is the cam drive pulley. So this is what the cam belt actually drives. We've only got one cam sprocket for 2 cams. So the advantage with this is it allows quite a narrow cylinder head design, keeps the packaging nice and neat. And there are some implications there around valve angle as well, but probably a different discussion for another day. So instead of being driven directly by the cam sprocket, the exhaust cam, which is this one over here, is driven off this helical cut gear. So this is what's referred to as a scissor drive arrangement. Now the problem with this is anytime we've got gears like this, inevitably we must have some amount of backlash, and if this isn't dealt with correctly, you're going to end up with a really horrible noise coming from those gears. It's basically they bang backwards and forwards together, taking up that lash. So Toyota dealt with this. It's a little hard to see possibly in this shot, but on the exhaust cam there, the gear is actually split into 2 pieces, and it's basically sprung loaded. And the idea there is that spring pressure takes up the backlash, allows the backlash to still be there, which is essential, but it stops the cam basically rocking backwards and forwards and making a hell of a lot of noise. So the reason I bring this up is that particularly on any of these scissor drive cam engines, people who aren't aware of this mechanism, you can come unstuck if you don't know how to deal with it. The problem is that if you just simply take those cams out, what's going to happen is that spring-loaded section is going to spring as far as it can. And while that's not unrecoverable, if you don't know that's happening, you go and put it back together, it's not going to work how it should. The spring-loaded mechanism won't be taking out that lash, and you end up with an engine that sounds like it's run a bearing sitting there at idle. So what you want to do instead, before you take everything apart, I'm actually looking at the wrong side of it from here, but there is actually a little threaded hole through the cam sprocket, and if you grab an M6 bolt and thread that through before you take the cam out, what that's going to do is hold the sprung loaded section of the cam gear in place, making sure it's not going to move when you take the cam out. Go and put it back into the same place, and everything's going to be nice and easy for you. So a simple little tip. Now, the other thing that this really comes down to is if you had read the factory workshop manual for the engine, all of this is detailed in the workshop manual. And this is something that I talk about quite a lot, particularly in our engine building courses. Before you start building an engine, it's really important to actually source a copy of the workshop manual. There's always going to be some intricacies with particular service procedures with different engines, and that workshop manual is going to give you all of those special service procedures, as well as giving you all of the clearances and all of the torque values for all of the fasteners in there. So it's an essential place to start. Probably getting on a little bit here, but I'm just about done. We'll just head across to our YouTube channel, and again, there's been a huge amount of content that we have punched out over the last 5 or so weeks, particularly because we've had our video crew all working from home, and considering we couldn't create any more content, they had the opportunity to basically get through our backlog of content. And this is actually one of the last videos we shot for lockdown here in New Zealand. We headed over to Australia to the Sydney Jamboree, which unfortunately was rained out, so it was a bit of a non-event. And we did get the chance to catch up with Rod, who is from New Zealand as well. I think at the time we were talking, he was number 4 in the world for 2JZs in terms of ET, and maybe number 3 in terms of mile an hour. That all changes, so if I haven't quite got that right, don't lynch me in the comments. But basically, this is one of the fastest 2JZ powered vehicles on Earth, and it's pretty unusual to get someone who's going to openly tell you some of the intricacies on what makes that car so fast. And Rod did a really good job here. He's given us a lot of insight. One of the particular things we focus on the side of this video, which I found really interesting, is that the car doesn't actually run a wastegate at all. Instead, it uses a drive-by-wire throttle body that's mounted off the intercooler. In fact, I'll just dive back here because it is pretty cool. I think we can just see it here. Yeah, we'll just pause here. So this little mechanism down here, that's a small drive-by-wire throttle body, and what it does is it actually feeds air back up through here and back into the turbo inlet. So Rod uses this on the line to control boost for the 2-step launch control, and then essentially by the time he's at about the 330 foot mark, that throttle body is completely closed and he's feeding the engine all of the boost pressure it can take. So again, if you want to know more details, head across and check that out. If you haven't already subscribed to our channel, give that video a like and ask any questions in the comments, and I'll be happy to jump in there. But as I've said, we've punched out a huge amount of content, so have a look around and have a look at some of the other videos that we have released. Lastly, before we get into today's webinar, we are running another one of our giveaways. We've only got 2 days left for this to go. So this is for an HP Tuners MPVI2 interface. You're also going to get $350 worth of universal credits, and you're going to get a training course package so that you'll know what to do with it. The HP Tuners platform now supporting quite a wide range of cars. It used to be fairly narrowly focused on Ford and GM. These days, that's out the window. There's access to all sorts, including Mercedes, Nissan, Toyota, Volkswagen, Audi, etc. So if your car is supported, this could be a really great way to get you up to speed learning how to tune that. Now, probably just throwing Scott or Jono under the bus there, but hopefully they'll be able to put a link in the comments that you can follow. As I've said, 2 days left to get your name in the draw, so you're going to have to move pretty quickly to grab that package. And it doesn't matter where you are in the world, we will ship it to you. All right, that brings us to the end of our pre-show. Thanks for joining us there. Give me a moment and we'll get started with our webinar.
If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.